I think we've got a nice segue from this presentation to research. So the first speaker in the research stream is going to be Dr. Jennifer Stansby. Jennifer is currently stuck behind a few people and is trying to get through. Jennifer works at UNSW. She's a postdoctoral research assistant in the nuclear research group. A chemist by training, so we moved from physics to chemistry, and did her PhD in battery materials, energy storage materials, and has become an expert in very advanced characterization tools. And now, hopefully, will tell us about how she's using these characterization tools to solve some of the nuclear challenges ahead. Please welcome Jennifer.
Great, thanks Patrick for that introduction. So before I begin, I'd just like to acknowledge the land that we're on today, the Gadigal people, and pay my respects to their elders, past, present, and emerging. So you've heard a lot from Patrick, but what about my perspective? Who am I, and why am I here standing talking to you today? So I'm a postdoctoral researcher in the School of Mechanical and Manufacturing Engineering at UNSW. By training, however, I'm a chemist, so I completed my PhD, as Patrick said, on energy storage materials, and have since transitioned to working on nuclear technology. So for me, climate and the environment is really important. And, you know, as a scientist, I could have stayed in the field of energy storage. I could have transitioned to renewable energy, worked on solar and wind. But right now in Australia, I think nuclear is a really exciting field to be in. And there's a lot of potential of growth, a lot of challenges to overcome. And also from a scientific perspective, lots of discoveries to be made. So my research focuses on nuclear fuel. Nuclear fuel is the material that is placed inside the nuclear reactor to produce heat. That heat then is used to produce steam, turns turbines, and generates electricity. And it's the fission of uranium which generates that heat. So the most widely used nuclear fuel at present is uranium dioxide. So my research is trying to find alternatives to uranium dioxide, better alternatives. And one of the most promising candidates at the moment is uranium nitride. So if we think for a second about the chemical formulas of those two fuel materials, we've got uranium dioxide, which has 1 uranium for every 2 oxygens. Whereas with uranium nitride, we have a 1-to-1 ratio of uranium to nitride. So that means we've got a higher density of uranium, the component that's responsible for the heat production in uranium nitride fuel. So that means if we want to produce the same amount of electricity, we can use less nuclear fuel, which leads to the production of less nuclear waste. So that's great. And you're probably thinking, well, why aren't we using uranium nitride in our reactors at the moment? And so the caveat is uranium nitride is known to corrode in steam. So when we're talking about pressurized water reactors, which are nuclear reactors that operate at moderate to high temperatures under pressure, this becomes a problem. And that's because in a scenario in which there's an accident or a defect in the nuclear reactor, the fuel could become exposed to steam. And in that scenario, it's really important that the structural integrity of the fuel is maintained, because otherwise we could get contamination of the fuel into the water coolant system. So researchers have been able to identify that upon exposure to steam, uranium nitride corrodes to, or breaks down to produce uranium dioxide. And they're able to do this through ex situ characterization. So they can characterize the starting uranium nitride material, subject it to steam, and then characterize the material at the end of the experiment. What is not known is this process in the middle. So how do we get from that start point to the end point? And that's where I come in. So with advanced characterization tools that we've developed that are here in Australia. It's the only place in the world where we can perform in situ neutron diffraction experiments on nuclear fuels to figure out what is that mechanism of corrosion and even obtain information about the rate of that corrosion process. And that's really important because with that technique, we can then explore ways of improving the corrosion properties of uranium nitride. So chromium, for example, widely used in many materials to improve the corrosion resistance. But interestingly, in this case, chromium has been found not to improve the corrosion resistance of uranium nitride upon exposure to steam. And instead, if we add zirconium, it does. So, why is this? And some of the results that I'll show later will tell us why that's the case. So to perform these experiments, we make use of facilities down at ANSTO, so the Australia Centre of Neutron Scattering down in Lucas Heights. And so what we do is we place our nuclear fuel material inside a stainless steel sample holder. And then we focus a beam of neutrons on the sample. It's really important that we can use neutrons for these experiments because unlike X-rays, neutrons are highly penetrating. So they can pass through that stainless steel holder and still interact with the sample, and we can detect the signal. So the neutrons that interact with our sample, different atoms are going to interact differently with the neutrons, and then we collect the scattered neutrons that come out the other side. And that can tell us about the type of atoms and location of atoms within our nuclear fuel. So this here is an example of the data we collect from these experiments. So along the x-axis there, we've got a wave vector which describes the neutrons that we're collecting. And then on the y-axis here, we've got the intensity. So how many neutrons of a particular energy we're detecting. Important things about this plot is that we can figure out exactly what materials we have in that fuel pellet from the peak positions. And from the intensities, relative intensities, we can figure out at any particular point in the reaction exactly how much of each material we have in there. And the really unique thing about the work is that it's in situ. We are monitoring the corrosion process in real time under conditions that are replicated from what would happen in a nuclear reactor. And so we're collecting lots of this data, and we can see changes in those peak positions, and those changes tell us how quickly the uranium nitride, for example, is being converted to the uranium dioxide. So jumping back to what I mentioned about this corrosion resistance with chromium added, these plots are showing us the rates of that corrosion process. So what we can see is at the temperature of 400 degrees C on the left, the corrosion process is slower in the chromium-containing sample than the pure uranium nitride. But when we jump up just 30 degrees to 430, we see that the corrosion with the chromium sample is really taking off. And so using this in situ technique, we can actually figure out why. And so by identifying the materials that are in that fuel pellet, we can see that the chromium isn't actually going directly into the uranium nitride. It's forming this secondary phase that you can see in blue there at the top, the uranium chromium nitride. And so if we look at the 430 degree plot there, It's the uranium nitride component that is being preferentially oxidized over the material that contains that chromium. So this led me to think of this hypothesis. Well, maybe the key then to improving the corrosion resistance of uranium nitride is finding an additive that is going to go directly into the uranium nitride matrix and just form a single phase fuel pellet. So we went away with our collaborators, tried a few things, and came across this zirconium sample. And this is amazing. You can see in the data at 400 degrees C, we're not even getting any oxidation of that uranium nitride fuel pellet with the zirconium additive. And even at the higher temperature of 430 degrees, there's a little bit of corrosion happening, but it's at a much slower rate than the uranium nitride. So where next? We've identified that we can improve the corrosion properties of uranium nitride fuel by adding zirconium. What we then want to do next is see, well, if the whole point of this uranium nitride fuel is that it's higher density than the uranium dioxide that's currently used. So how little zirconium do we need to add to still get those benefits? Another area that we're going to explore as well is how do the corrosion processes change to a fuel that has been in a reactor for, say, 3-4 years already? Is that going to be the same? And we can do that by simulating the fuel having been in the reactor by doping it with elements such as molybdenum and niobium. So with that, I would just like to say a huge thank you to a really big team that has made this research possible. So at UNSW, I'd like to thank Edward and Patrick for their continual support. It's really encouraging and motivating to see the amount of time that they're willing to spend on training up young researchers like myself. There's then the team at ANSTO with a special mention to Vanessa. So Vanessa is an extremely successful and talented beamline scientist, and it's been really inspiring to be able to work alongside such a successful female scientist, and I really hope one day in the future I can be that role model for females wanting to become nuclear engineers. I'm also very fortunate to work with Josh and Elizabeth, so they're based in America, and they're the world leaders of fabrication of high density fuel pellets. And next year, I'm hoping to go over there and learn from the best how it's done and bring those skills back to Australia. We've also got the team over in Sweden, so Denise, Julia, Sobhan, and Per, and they're the experts in ex situ characterization. So here in Australia, we're really leading the way with the in situ characterization, so the real-time monitoring of how the corrosion processes happen. Over in Sweden, they do a lot of thermophysical measurements, and I'm also hoping to go and visit their labs, and together we can plan out some more directions for my research in the future. And then that just leaves me to thank you all here today for your time and attention. And if you've got any questions, I'm happy to answer them in the break, or would love to chat to you at some point today. Thank you.